This lesson is going to continue our discussion on trends on the periodic table, but this time we're going to look at two other trends. One is electronegativity, and the other one is reactivity on the periodic table with both metals and nonmetals. First, we're going to take a look at electronegativity. So what electronegativity is, it's a numerical value, and it's going to measure an atom's ability to attract electrons when forming a chemical bond. So there's two types of compounds we're going to look at in chemistry. There's ionic and covalent bonds that form. That's going to be coming up next in our discussion about the atom. But when two or more atoms come together to make bonds, they do different things with their electrons. Some give them away, and then some share them. Some share them equally, other ones share them unequally. So this value of electronegativity gives you an idea of how that sharing is, and it is a numerical value. It's on your periodic table. If you take a look at the one that was posted up, you can find the actual value on your periodic table. So what's the pattern with electronegativity? Just like we were doing in the previous lesson, we're keeping our direction on the periodic table the same. As you go up and as you go across, this value of electronegativity increases. So an increase in electronegativity. So lowest down here and the highest values sit up here. So why is this happening? The biggest driving factor with this is thinking about metals and nonmetals and where you can find them on the periodic table. So remember, nonmetals are found to the right of the staircase. So if we draw that in here, over here you're going to have your nonmetals. And over here, you've got your metals. And then along the staircase down here, you would have your metalloids, elements that have properties of both metals and nonmetals. Okay. And when we look at metals versus nonmetals, there are some differences between them. So when nonmetals form bonds, they accept electrons. They want them. When nonmetals form bonds, when metals form bonds, they don't want the electrons, they give them away. They donate them. So when we think about ions that they can form if they were forming different types of bonds, metals like to form positive charges and nonmetals prefer to have negative charges. So if we go back here and look at these explanations, nonmetals accept the noble gases. They're going to attract electrons when they're bonding, and they're considered electron acceptors. What that does is it gives them a higher value for electronegativity. So if you take a look on your periodic table and you go and look at fluorine, for example, in the top right-hand side, it'll have a high value of around 3. And if you compare it to nonmetals on the other side, they're going to be less than 1, often less than 0.5. They can be very small. Metals do the opposite. They tend to lose their electrons when bonding, so they give them away, or sometimes they're called electron donors. They are the ones with lower electronegativity values. We're going to continue on and talk a little bit more about metals and their reactivity and some specific areas on the periodic table where you do see some patterns or trends happening. So what's reactivity? It's how likely an atom is to react with other substances by either gaining or losing electrons. So when we think about metals, metals have the highest reactivity in group 1. Those are your alkali metals, and the reactivity increases as you go down. So if we flip back to this previous periodic table we were looking at, this group here is your alkali metals. Not hydrogen, it's not a metal, but starting here at lithium. And as you go down that periodic table, the reactivity increases, so most reactive. In general, the larger metals tend to be more reactive than the smaller ones. There are also metals in here in the transition block, but their reactivity varies. So we know metals are here, the transition metals. Their reactivity is lower, but it's not consistent. There's not necessarily a pattern in here. If we go back, and now we're going to look at nonmetals, there's also a trend with nonmetals. So what you see with nonmetals, in group 17, which are your halogens, they have the highest reactivity out of all of the nonmetals. In the halogens, the reactivity increases as you go up the group. So if we go back to that periodic table, this group here are your halogens. And here the reactivity increases. So halogens start here and going straight up. Here, fluorine is the most reactive and iodine would be the least reactive. So that pattern goes opposite. You can see with the nonmetals, it goes up, and the metals, it goes down in terms of reactivity. One other thing to point out, there's one more group with reactivity that's important to note. Those are your noble gases, which are in here. Noble gases, make a note down here. Okay, that group we know is non-reactive under normal circumstances because all of their outer electron shells are full. So when you do your diagrams for Bohr-Rutherford, they always fill up 8 at the end. They don't want to gain or lose electrons. They're nice and stable, and that's why they're not reactive. So let's talk a little bit more about why this is happening. So when we're talking about metals, the further to the left and down you go, so down at the bottom of the alkali group, you find it's easier for the electrons to be given or taken away. That's where we get higher reactivity. There's a larger atom size. The electrons are further from the nucleus. And so remember those protons, when we talked about the other trends, were important. Here, those electrons, you don't really feel them pulling nearly as much on those electrons, so they're easily lost. With nonmetals, it's a slightly different situation. So as you're going up and across towards fluorine, you'll find that electronegativity values are higher. And that means that they really want those electrons. They're also smaller atoms. We know that the trend is atomic radius decreases as you go up and across, so it follows the same direction. And because there's a smaller radius, they can feel that pull from the nucleus and the protons as well, so that also helps contribute. So let's try out a problem and see if you understand these two trends and how they relate. Metals and nonmetals and their reactivity and electronegativity. So which element is more reactive, lithium or potassium? So with this question, first you want to decide, do I have a metal or non-metal? When we think reactivity, we know it's a little bit different for metals and nonmetals. So if we look, lithium and potassium on the periodic table, they are to the left of the staircase. They're both alkali metals. So that's the first thing I would want to think about before I start trying to make any conclusion. Okay. Then if I know I have alkali metals, I know there's a pattern with alkali metals. We know that alkali metals, their reactivity increases as you go down. And then you have to look, well, which one is higher and which one is lower? So lithium is higher up than potassium. So we know lithium will be less reactive and potassium will be more reactive. But then you want to think about why. So we've kind of broken down where we can find these elements. Are they metals, non-metals, using our placement on the periodic table? But why? What does higher and lower in that family actually mean? So at this point, what I'd recommend, pause the video and draw out the Bohr-Rutherford diagrams for both elements, for lithium and potassium. Once you have those drawn, unpause the video, and then we'll take a look at those diagrams, and hopefully that'll help put a few pieces of the puzzle together. All right, so let's take a look at some practice with the Bohr-Rutherford diagram. So same question, but now we've got to explain why. We said this is less reactive, and this one's more reactive, but why? Why is that happening? So the first thing you might notice, lithium is smaller in size compared to potassium is larger. You can visually see, which is why it's helpful to draw these out. There's two energy levels here. And over with potassium, there's 1, 2, 3, 4. When we talk about reactivity for metals, the electron that's going to react is the one that's the furthest away and that's on the outside. So they both have 1 in their last orbit in their Bohr-Rutherford diagram. So that's the reactive electron. So both can react and they both will. But what makes potassium more reactive is the fact that this electron is further away from the nucleus. So here's the nucleus and it's 4 levels away. When you compare it to lithium, it's only 2 levels away, so it's closer to the nucleus. And just so we're clear, the electron that we're talking about is this one, that particular electron. So since this one's further away, it doesn't feel the pull of the protons as much, so it's easier to pull away. This one over here is harder to remove and harder to react because it's closer to the nucleus and feels those protons. So when you're thinking about trends with reactivity and electronegativity, think about whether you have a metal or non-metal, look at their electron arrangements in your Bohr-Rutherford diagrams, and tie in those concepts we talked about before: atomic radius, the nuclear charge of the atom with the protons. You can even use ionization energy as well to help explain. So those are all things that are really helpful. To see some of these elements in action on your own time, I'd recommend watching this YouTube video. The link's also posted up in our lesson folder, and then you can see the differences in the alkali metals and their reactivity.